Good evening. Okay, so this was an interesting question to me, posed by one of the students while I was teaching the circular motion. He said, Sir, I was teaching circular motion and I started with the tension, velocity, and so on. Then said, Sir, circular motion is also a two-dimensional motion, right? I said, yes. Then if that is the case, why can't I use equations of motion? Yes, okay. Why do you think it should happen like this? And said, Sir, anyway, the tension is there. Sorry, the circular motion has x and y coordinates, similar to the projectile motion. So why shouldn't I use it? Let me show you what does it mean. And it took some time for me to understand why he had this notion. Okay. So in a projectile motion, what we do is we throw a particle like this. We throw a particle like this. It takes up a path like this and comes over here. While we do this, what we assume is it's my x-axis, this is my y-axis. And there is a constant gravitational force always acting on it. The acceleration due to gravity is always same at all points, is what we assume. Now, what he said was that if you can assume something like this, in case of a circular motion, you have this is your fixed end, then you have an object here, you give a push here. As a result of it, instead of doing like this, it goes like this. So why can't I assume? At every point, once again, you have a g here. You will always assume g here. And as a result of this, you should definitely be able to use your equations of motion because g is constant. Then I thought for a while, then realized where it went wrong. The misconception that student had was that when you consider the net force acting on this object at this point, this is your mg. Just a minute, let me reshare. I just came out of the path and just a moment, let me reshare it. Right. Okay. Here. Okay. So therefore here it is mg here and there's a tension here. Now what do we generally write here? Okay, we don't write T is equal to mg here, right? We just write T minus mg is equal to mv square by r. That's what we write. Now when I hit this with a velocity v, I give some energy to it. Now as the particle keeps on going, this v keeps on reducing. When this v keeps on reducing, automatically this T minus mg will also reduce. What is this T minus mg? It is nothing but the net force. Net force keeps on reducing. Now here what's happening? Your net force is always mg, but here net force is reducing. When the net force is reducing, which means your acceleration also reduces. When your acceleration is reducing, then automatically acceleration is varying. Can you use equations of motion here? You cannot use. Reason is because equations of motion should be used under what condition? Under what condition? When the acceleration is constant. What do you mean by acceleration is constant? Which means its magnitude and the direction both are constant. Now here you see the magnitude is always equal to 9.8 and the direction is always downwards, whether the particle is here, wherever it is. And here you see the net force, initially here it is directed like this. Here it is directed like this. Here it is directed like this. Everywhere it is changing like this, right? So direction is not constant. What about the value of the A? The value of A, say for example here, where did I write? I wrote here, net force is mv square by r. Okay, so therefore acceleration is equal to v square by r. Though r is constant, v will be changing. As it keeps on going, the velocity should change, right? Do you agree? The velocity is changing. It's not like in your horizontal circular motion where you have a uniform circular motion here. Okay, velocity is definitely changing. If velocity is changing, then in such cases, acceleration or the value also changes. So magnitude is also not correct. So magnitude is not constant, direction is not constant. So your equations of motion should not be applied. I hope You got a clarity on this principle. Okay. Thank you. Thank you for watching this video. So if you like this video, do subscribe to my channel for further updates. Thank you.